let me first stress again that, oh God, why is that happening? Never mind. That optical fibers is actually a British affair. From John Tyndall in 1870, where he first demonstrated that actually a water jet, when light is shown through it, guides the light. The light doesn't go straight through. It follows the flow of the water. And I will explain a little bit more about why that is. But that was the first demonstration of actual light guidance, which led us to optical fibers. And Charles Cow, the last year's Nobel Prize laureate for groundbreaking achievements concerning the transmission. I'm sorry, this is doing things on its own. Achievements concerning the transmission of light in fibers and optical communication. Now, what is the optical fiber? Why is it doing that? He wasn't doing it earlier. Never mind. I thought that, for the audience, I think it's going to be a good idea to explain what a fiber is. The fiber is a strand of glass, the size roughly of a human hair, and some of us have thinner hair than others, but that size roughly. But it consists of a core, which is glass of larger density, and a cladding, thinner glass, thinner density. And that interface between the thick glass and the thinner glass actually is what causes the total internal reflection and traps the light as it propagates through. So now light is trapped and can go around the corners, and as we've seen earlier, it can go all around the world several times, and is the basis of the Internet. Now, the Optoelectronics Research Centre in Southampton, we believe is the largest photonics group in the UK, roughly 150 staff and PhD students. It has a long history. Success does not come without history, without successful history. And in Southampton, we've got a 40-year history in cutting-edge fiber research and technology. And I'll give you two examples of that sort of fiber technology. Actually, we claim, and nobody's disputed that yet, that all the special fibers that have been designed to very, very efficiently do a particular job, all these fibers have come out of Southampton. Nobody has disputed that yet. And two noticeable examples is the optical amplifier. It was earlier said that fiber and lasers were the key components of Internet. Actually, the optical amplifier is what really made it possible, okay? Each time you make a phone call, you send an email, you download a file, you go through an optical amplifier somewhere in the world. And of course, the fiber laser, which is what I'm going to be talking about, is the latest sort of innovation. It's an old innovation. It was developed in '87, but now it's been transferred out into the real world and is making a strong impact. Oops. We are very, very thankful, of course, to EPSRC for a very, very generous funding. 33 million, the current funding for the next 5 years or so. We also supplement that with 1.5 million of EU funding and roughly 4 to 5 million of industrial. This is not as high as we would like to be, but we are working very, very sort of intensely around that to improve that sort of figure. We produce roughly 270 publications per year. The quality is reflected by the fact that 50 or so are invited and plenary talks, but also very, very important for this meeting, we produce roughly 11 patents per year. We are responsible for 50% roughly of the IP, of the entire university IP. And that is supplemented by very strong industrial and university links and a very extremely strong worldwide 650 staff alumni. This is very, very important. All the photonics, we can say that safely, all the photonic companies in the world have some University of Southampton ORC member in their teams. And the IP generation is reflected into the photonics cluster that I'm going to be talking about. 10 companies in the area of Southampton, they are listed here, where they produce roughly 100 millions of pounds per year, turnover, and they employ in excess of 500 people in the area. In addition to Fianium and SPI lasers that I'm going to be talking about, which are fiber lasers, we have sensor and smart fibers that do sensors work. Also, mesophotonics or stratophase, we do much more innovative, forward-looking products using photonics, not necessarily fibers. So what is SPI, Southern Photonics Inc., SPI lasers? I'll talk about the core technology and how that is being, oops, again it's doing it. The core technology, the markets, and a little bit about the products and the applications. More of that we can talk about later. So SPI is a spin-off, Southampton University OASIS spin-off. Actually, we can say, oh, this is a little bit crazy. We can safely say it is the most successful OASIS spin-off. Raised $55 billion in 2000. The interesting story behind this is that the company was initially set up to address the telecoms market. But of course, in 2000, the telecoms market, we all know, collapsed. So we were left with a company with a very exciting and novel products, but no market. That's a very, very sort of precarious situation to be. But it was this next bullet point is very important. We were licensed 24 patent families from the university that enabled the company to redirect ourselves into a new market, industrial laser market, which was a blooming, real market, very, very strong. So we could very quickly reposition ourselves and address that new market. So it's very important when you go to the university to get access to IP, the university has to be generous to you, okay? The company was acquired by Trumpf. Trumpf is a German company, but is the leader in traditional laser systems manufacturing. Most of the huge industrial laser systems are made by Trumpf. And now, currently, SPI is a leader in fiber laser technology and applications, one of the leaders. It's a real company. It's got 5,000 square meters of facilities, of which 15,000 is clean rooms in Southampton. And we are dealing with all aspects of fiber laser design and manufacturing. We make lasers, real lasers. We employ currently 200 employees, and that's on the up. We are planning to increase the count in the next year or so. What is a laser? Very, very briefly, it's running again on its own. Never mind. It's I'm putting this slide to show how simple it is to put a laser together. It's a piece of fiber, and in order to make a laser, you have to have a cavity. So basically, you have to put two reflectors on either side to form a cavity, and basically control the photons, herd the photons inside that cavity. This then is pumped with the type of lasers that the previous speaker talked about, the pump lasers, and light is being regenerated within the fiber and comes out from the other side. But the trick here is that the beam quality is much, much, much better. So it's a beam transformer, if you like, the fiber laser. You get dirty photons, cheap photons, that they're in abundance and very easy to produce, and turn them into very high quality photons, very well-directed photons. And it's the beam quality and the efficiency with which you do this transformation of photons that gives the fiber lasers, okay, the edge. But having said that, all the innovation and complexity goes inside the fiber. You have to design it properly. You have to make it properly in order to get this simplicity. And the ORC has provided the company with the two main sort of IP elements, the two patents, which are very, very critical for building this cavity and having very strong protection worldwide. Where are the lasers right now? We are in the, if we look at the power versus time, we are in the 6 kilowatt or more peak power coming out of a single fiber, okay? And to give you an indication of what that means, this, if we take the kilowatt laser, this gives you an intensity of 5 × 10⁻¹² watts per square meter, which actually for people that are not aware of those units, is 100,000 times hotter than the sun's surface. So now you can see why these lasers can have such an impact in industrial applications, metal cutting, metal welding, etc. You have to have a market in order to be successful. And this is the projections of the market, of the total available market, in excess of $3 billion in 2013, 2014. But the fiber laser is started with 5% of that market share, and now is projected to get 21% of that share. It's interesting to see that when the ditch in the economy happened, actually the fiber laser hasn't been affected that much. It was the new technology that people kept investing into. Very quickly, one application of the fiber lasers, this is just one fiber laser, okay? It's 200-watt laser, not the full range of lasers. And you can see established applications in medical device, cutting and welding, automotive competitive welding, rapid manufacturing, engraving, disc drive spot welding. All this stuff now is done with fiber lasers. And there is coming up the applications, cutting thin films, solar panels, ceramics, etc. And I've got one, if it works, yes. This is fiber laser in action. This is a fiber laser at the end of the robotic arm where it welds parts of a car. As you can see, it can be done really fast from a distance using robots, and this is because of the beam quality and the intensity of the laser, of the beam coming out of the fiber laser. So very quickly on the future, Southampton still runs on a very high fiber diet. So we're producing all sorts of different fibers, square fibers, Swiss roll type structures. Now, fibers suspended in air or having concentric rings of very different materials. So the choice of material you're using is very, very important for applications. And this type of materials, the high nonlinearity materials, are very exciting. We are working on them. We believe is a solution looking for a problem, but we continue with more complex fibers, ones with holes around the core or inside the core, with semiconductors embedded into the fibers, helical core, nanonodes based on fibers for sensor applications and other nonlinear processes. But based on the 100 million new facilities that are now up and running in Southampton, we do much more than fibers. We are working on nanoparticles, on microresonators, using those nonlinear materials like the chalcogenides for memory films, or for all optical switching. Switching actually is what's missing from this sort of huge telecom internet network, like all optical switching. All the switching right now is happening in the electronic domain. Signals have to be transferred from photons to electrons back to photons. And that's a very, very costly process. It contributes into 4% to 5% of the total energy being consumed by the internet. So this, well, the optical switch, all optical switch, is the holy grail of the future network. Nonlinear crystals, but also other non-telecom applications like photonics biolabs, where all the circuitry, the optical circuitry, is designed on a single chip. And to finish off, we make a very, very big effort to retain the ORC at the forefront of photonics research. We combine a unique academic excellence, science, engineering, and commercial activities. We have demonstrated a strong track record of successful commercialization of the research coming out of our labs, and we intend to continue doing so.